This is now we examine probability experiments where the outcome of a particular value of a quantity is, the outcome is a particular outcome of a quantitative variable. So basically the outcomes are always a number and the number is always a quantity. Okay, and you'll see an example here. The variable is always denoted by an X, but sometimes I said always, usually an X. It represents all possible outcomes for a random trial or an observation. The probability of observing a particular value of X is denoted P of X down here. Okay, any questions? Now, for a discrete random variable, this is one whose values are discrete. We talked about discrete values. They're ones that you can count. A variable whose values you can count or at least list in order. So discrete random variable, the values can be counted or listed because there are gaps between possible values. Yeah, so for example, the X could take on values of 0, 1, 2, 3, 4, 5, etc. Each of those values has a gap between 1 and the next. So between 1 and 2, there's no value that is possible for this variable because it's something you're counting. So if you're counting, the number of people, there's not going to be 1.5 people. So those are gaps between possible values. And then the probability distribution is where for each value of X, we associate a probability. Which will be P of X. Okay, and so you can see down below on the handout that there's a table where I'm going to have a bunch of different values for X, and then I'm going to figure out the probabilities for every outcome. There's a couple other columns that we'll fill in later, but we're just going to build a probability distribution. So the example, and again, probability distribution is where you associate to each value of the variable a probability. So when you toss 4 coins, we're going to let X represent the number of coins that land heads. Okay. Now remember, a sample space is just a list of all the outcomes. So let's see here. You could get 0 heads, so that would be 4 tails. Okay. You could get 1 head. That could be HTTT, or tail, head, head, tail, head, tail, tail, or tail, tail, head, tail, or tail, 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 head. So all of those are with 1 head. I'm going to kind of highlight those together. Okay. You could get 2 heads, so you could get HHET, or head, tail, head, tail, or head, tail, tail, head, or tail, head, tail, head. And all the different ways you can get 2 heads. Or tail, tail, oops, head, head, You guys, there's one more way to get 2 heads that I missed. Can you see it? Can somebody type it? I missed one of the ways to get 2 heads. Tail, head, tail. Thank you, Jason. Correct. Okay, so these guys all go together. I'm going to highlight them with a different color. Those all have 2 heads. Let's do 3 heads. So you could get the first 3 as heads and then a tail, or the tail could occur on any of these outcomes. So you could do head, head, tail, head, or head, tail, head, head, or the first could be the tail, tail, head, head, head. So that's with 3 heads. There are no other ways to get 3 heads. So I'll highlight those separately. And what's the last thing that I need to list here, just in terms of heads and tails? All heads. So the very last one is H, 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 like that. Yeah. Okay, so now my random variable X is the number of heads. Okay, so down in the table here, I want to list all the values for X. What's the first lowest value for X? Again, X is the number of heads. What's the lowest value for X? 0, correct. You could get 0, 1 head, 2, 3, or 4 heads. Okay. Now the probabilities. First of all, what's the total number of outcomes when you toss 4 coins? Each one of those outcomes up above is one of those. Total of the outcomes. What's the total number of outcomes? I don't mean individually. I mean the tail, 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 tail is one outcome. Yeah, there's 16 outcomes, Andrea. Thank you. Total outcomes are 16. So what's the probability of getting a 0 heads? One out of, remember probabilities you have to divide. 1 divided by 16, I think, yeah. Good, so I'm gonna put in the probabilities. So there's only one way to get 0 heads out of 16. What's the probability of 1 head? Yeah, 4, but you gotta say 4 divided by 16, which is 1/4, correct? But I'm gonna leave it as 4/16. 2 heads, I think, is 6/16. Okay. 3 heads goes back down now, 4/16. And 4 heads, there's only one way to do it, so that's down to 1/16. Okay, I'm going to pause for a second. Does anybody want me to explain this better? And when you list all the probabilities, you're describing how the probability is distributed among the outcomes. So again, that's a probability distribution. What do you think those probabilities add up to? Anybody? Yeah, 16 out of 16, which is 1. Oops. So the total is 16 out of 16, which is 1, and 1 is the same thing as 100%. Okay. So the question down below is, what's the sum of the probabilities? It says 16 out of 16, which is 1, or 100%. So that's why we sort of call this a probability distribution, because you're taking that total 100% probability and you're looking at all the outcomes and you're sort of distributing it amongst the outcomes. And in most cases, probabilities don't get distributed uniformly. They sort of have uneven probabilities. And you can see that here. The most probable outcome here is 2, which has a 6 out of 16 probability. Looks like we have to compute these on our calculator. So 1 divided by 16 is 0.0625. So I'm just going to put that in next to all this. 4 out of 16 is 0.25. 6 out of 16, I'm guessing, is 0.375. 4 out of 16 again, 0.25, and 1 out of 16 again, 0.0625. Okay, and we want to go ahead and graph these now. So all right, so I'm just going to do the heights of the bars. This is just going to be a histogram. So the first one's 0.0625, about that high. The next one's 0.25 right here. Next one's 0.375, gonna go right about there. Then going back down to 0.25. And back down to 0.0625. Just a little more than halfway up on that first line, like that. And then this is a histogram. Sorry about the noisy guys. That's our little bar graph. It says the bars should touch. Remember, histograms have touching bars, and there's a reason. I'm just going to give you guys a second to catch up. Coloring is sort of a great thing to do during pandemics. It sort of comforts you a little bit, so I like the color. The world is falling to pieces, but at least I have my colors. Anybody want to ask a question? No, 16 is the number of tosses. So I don't know if you guys see that question by Susan. When you think of outcomes, we're talking about the outcome. There's different ways of describing what the outcomes are, right? So right now, it was predetermined. I already knew I was going to toss 4 coins. The fact is that there are 16 outcomes. That's 16 arrangements of the 4 coins. Why wouldn't 16 represent the number of possible outcomes? It does. Okay, 16 is the number of possible outcomes. But when you say, what's and that's in the sample space. But right now, I defined X to be the number of heads. So the outcomes for heads are different for the outcomes for the number of heads is different for just asking, well, what are the possible tosses? So I guess it just sort of depends on what do you mean by outcomes. Right now, I'm looking at the outcomes for X, which was defined as the number of heads. Okay, and in that case, there's actually 5 outcomes. You could get a 0, 1, 2, 3, or a 4. Does that make sense? You're right. There are 16 individual arrangements when you drop 4 coins, but we're grouping some of them together. The one head happens in 4 ways. So that's an outcome, but it's not a simple event, it's a compound event. So I think, Susan, you're thinking of the simple events, which are the 16 things we listed up there. When I say one head, that's a compound event that we decided could happen in 4 ways. 2 heads also compound, so that happens in 6 ways out of 16. I don't want to sort of overthink this. I mean, we just listed that there were 16 outcomes up above here that I shaded in the different colors. And when I say, what's the probability of 2 heads, you just have to see how many of them had 2 H's and divide by the total number of outcomes, which was 16. Okay, and the only thing I'm really introducing is this weird variable X, which is counting how many heads there were. Okay, so I hope that helps. And don't worry about this too much, because right now it's just sort of in a theoretical realm, and in the end we're going to make this real practical. There's a question here about the total area of all the bars. So if you look at all these bars, they have a base, and I'm going to erase these notes, but the width of each bar is 1. And the height of the bar is the probability. Okay, so when you do the base times the height, that's just 1 times the probability. So the area of the bar is the probability of the corresponding event. So for 1 head, the probability is, what do we say up here? For 1 head, it's 0.25, but that's also the area of the bar. The area here is 0.25. The area is the probability. Okay, so the next bar has an area of 0.375. The next one's 0.25. The last one's 0.0625. That's the base times the height. And the height is the probability. Okay, the first bar is also 0.0625. So the question that's asked down here is, what's the total area of all the bars combined? Anybody want to take a stab at that? I'm gonna do a little cleanup on this. Pardon me real quick. Okay, so what's the total area? Anybody do it? Yeah, total area is 1. The total area is the sum of all the probabilities of X. Okay, so remember that's a Greek sigma. That means the sum of all the probabilities, which is 1. Okay, any questions about that? Now I think in your notes you have the formula for the mean from a frequency table, which is this one here. I think the only thing I would add is just, you know, we don't use that formula very much, but we can use that formula to convert it into a mean using probabilities. So if you just look at that formula, look what happens if you write it this way. This is the same result. If you wrote the f divided by the n like that, and then multiply by x, that's the same computation, just looks different. Okay, and when you think about f over n, that's just a relative frequency. Okay, a relative frequency is just the number of ways, number of times something happened divided by the total number of outcomes. So f over n, that was what we did with all of these up here. 1 out of 16, because there was only one way, that was the frequency, one way to do it out of a total of 16 outcomes. For one head, there were 4 out of 16 ways, so 4 ways to do it out of 16. Those are all relative frequencies, 4 ways divided by the total number of outcomes. So when I say f over n here, f over n is just p of x. So the mean for a probability distribution is just x times p of x. Okay, that's it. And so we'll be doing that computation in a sec. There's also a way to get a standard deviation from a probability distribution. You just kind of look at the graph. Whenever we see graphs like this, we're always saying, what's the center? Well, the center is the mean. And what's the spread? The spread would be the average distance from the mean, which is the standard deviation, which is just a measure of how wide that is. Any distribution of values has a mean and a standard deviation. And this is a distribution of probable values. We still want to know what the mean and the standard deviation is. So you can see the formula here for the mean, sorry, the standard deviation from a frequency table. And I'm just going to rework this a little bit this way. You've got this n in the denominator, so I think I'm going to write it as a 1 over n. You've got the sum of fx squared, and then minus a 1 over n also divided by another n becomes a 1 over n squared. Sum, oh, this is in parentheses, my bad. Sum of fx quantity squared, like that. And you could rewrite this way. The sum, you could, instead of having 1 over n, you can multiply that through with the distributive property and do f over n times x squared minus, watch what I do here, that n is being squared and the sum is being squared, so I can put it inside this way. I can do the sum of f over n x, and that quantity squared, like that. And then remembering that f over n is just p of x. That's just a probability. You can finish this up by saying, oh, well, that is just the sum of x squared times p of x minus, in parentheses, the sum of x times p of x, quantity squared. And then reminding you up above, the sum of x times p of x is the mean of the distribution. We use a mu for a population mean now. Okay, so that's the mean of the probability distribution. So I can say, oh, this is the sum, the square root of the sum x squared p of x minus the sum of x p of x, that's the mean up above, squared. So that's going to be the formula for the standard deviation of a probability distribution. And I've mentioned it in passing that variance is just the square of the standard deviation. So the variance of x is sigma squared. Now it's referring us back to the coin tossing experiment. It's asking for the mean and the standard deviation. So I'm just going to real quick remind you, the formulas are here. Okay? I guess I can copy them down here. The mean is going to be the sum of x times p of x, just from above, and the standard deviation, sum of x squared p of x minus the mean squared, and the variance is sigma squared. So we have to do these computations. But I'll tell you, when you do these by hand, anytime you see one of these sums in a formula, and there are two here, you want to add those up in a table somewhere. So that's why up above, I left two blank columns in the table. I've got an x column, a p of x column, but the mean needs a sum of x times p of x, so we need to add that up somewhere. And the standard deviation requires an x squared p of x that has to be added up as well. Okay, so you just multiply x times p of x. So on the first one, x times p of x is 0 times a 16th, which we'll just say is 0. Okay. Then 1 times 4/16 is, sorry, 1 times 4/16 is 4/16. Okay, then 2 times 6/16 is 12/16. 2 times 6 is 12. Okay. And then 3, oops, times 4/16, that's x times p of x, is 12/16 again. Okay, and then 4 times 1/16 is 4/16. Okay, so that's x times p of x. Looking to see if there's any questions about that. We've got to add them up. So 4 and 12 is 16, plus 12 is 28, plus 4 more is 32. So this thing adds up to 32/16. And I think 32 divided by 16 is 2. And I'm pausing to see if there's any questions. Okay, now the standard deviation requires that we do the sum of x squared times p of x. So that's the next column in the table. Just square the x and then multiply by the probability. So 0 squared is 0 times a 16th, 1/16 is still 0. 1 squared is 1 times 4/16 better be 4/16. So that's pretty easy. Gets a little more complicated now. 2 squared is 4, and 4 times 6/16. 4 times 6 is 24/16. Okay, now 3 squared is 9, and 9 times 4 is 36. That's 9 times 4/16 is 36/16. So these get kind of big. And then 4 squared is 16. And 16 times 1/16 is 16 times 1, 16 sixteenths. And then we need to add those up. And let's see, 4 and 24 is 28. 28 and 36 is 64. So 16, I think, is 80 divided by 16. Anybody want to take a stab and write down what 80 divided by 16 is? Yep, 5. Thanks, Susan. Okay, so let's just denote here, this first, the 2 was the sum of x times p of x. That was 2. And then the 5 was the sum of x squared times p of x. So again, that's 5. Somebody says, why 80? Oh, well, I just counted how many sixteenths I had in the last column, Johnny. So 4 and 24 is 28 plus 36, and that's where I did the math. 28 plus 36 is 64. And then there's another 16 80ths. Remember, when you add fractions, you just add the numerator. So I'm adding 4, oops, hang on. I'm adding 4 and 24 and 36 and 16 to get 80. And the denominators don't do anything when you add fractions. Johnny, you doing okay? Okay. Okay. So we've got our totals, and that's the hardest part about all of this, is getting these totals. Okay, so I'm going to just bring that back down here. And this one and the other one. Okay, I guess I should have brought that down lower. Okay, so the sum of x times p of x is the mean. So the mean is 2. That is a lot of work to figure out something that's absolutely obvious. If somebody says, drop 4 coins, what's the average number of heads? 2. No kidding. So we can go back to the distribution up here. And in the center of the distribution, right where the mean should be, is mu, the center of the distribution. Okay, totally obvious, but this also works in cases where the numbers are messy and it's not obvious. And that's really what's more important here. Okay, any questions? All right, next, the standard deviation. So we have to do the square root of the sum of x squared p of x. That's this guy over here I just circled. Okay, so x squared p of x, that's just a 5. Oops, just a 5. Minus the mean. Okay, the mean was 2. So it's 5 minus 4. That's easy. 5 minus 4 is 1. Square root of 1 is 1. So the standard deviation is 1. So the mean is 2, and the average distance from the mean is 1. Perfect. Variance is the standard deviation squared, so this will be 1 squared. So the variance is 1. Variance is important in the next section of the material. Okay, so going back to the next page, I just want to summarize what we've got here. So the first thing is that the probability of x is always between 0 and 1. This is just a summary of everything for this lesson. So I'll say for all x. Probabilities between 0 and 1. The next thing we figured out is that the sum of the probabilities is 1. So that you have this sort of, that's your pie, and you slice it up, and the way you hand out the probabilities to the different events is how you're distributing the probabilities. It's a probability distribution. Then I think the next one was that the mean is also called expected value. Now it gets a new name. Okay. It's also denoted E of x. So these are all different ways of saying the mean. Okay, the mean is the expected value of the variable x. Okay, and then the formula is, as we've used already, it's the sum of x times p of x, like that. And then the standard deviation is sigma. Okay, sigma doesn't have a special notation, it's just the standard deviation. And so the formula is, as it was, sum of x squared p of x minus the mean squared, like that. So standard deviation. I'll make some more notes into this. So the mean expected value is also known as the mean. Okay, and then finally, sigma squared is variance. And you will see in the next lesson why this is important. Right now, it's just the square standard deviation. But we denote, it's so important it gets a weird notation, var x. The variance of the random variable x is how I would say that. Okay, and I was supposed to cover one more lesson, so that puts us one section. Somebody said we were a week behind. We're only one section behind. If you look at the schedule. So today I was supposed to do, this was 5.1. Today I was also supposed to do 5.2. But we'll do that next Wednesday. Sorry, next Friday. Okay, so I'm going to turn the recording off. Okay, so this is section 4.2. Which is on what we call properties of expected value and variance. Just to remind you, expected value here, that's the mean, mu, and it's also called E of x. So mu is the same as E of x. And variance is sigma squared. That's the standard deviation of the population squared. So sigma squared is the variance of x. Okay, so let's go ahead and read this. It says, in this lesson, we established some algebraic rules for expected value and variance of a discrete random variable. These rules will soon have important implications as we develop important theoretical ideas. Yeah, it's just super interesting stuff to a math nerd, I guess I should say, that when you add two variables together, the means will add. If you multiply a variable, every value of a variable up by a number, the mean gets multiplied by that number, stuff like that. And so that's what we call the algebra of expected value. And similar rules hold for the variance as well. So we're going to go ahead and just start by demonstrating. The proofs are a little bit difficult for these ideas, but it's easy to just sort of illustrate how they work. So just demonstrating everything by way of example. So we have two very small populations. These are not samples, these are populations. And we just want to sort of describe everything here. So the values are 7, 9, 9, and 11. So I'm just going to do the values of 7, 9, and 11. Okay, and if I want, I can have a total row down here. Okay, so 7 occurs 1 time out of 4 in the population. So that's at 0.25%. The 9 occurs 2 times out of 4, so that's a higher probability. So that's 50%. And the 11 just occurs 1 time out of 4. So again, that's a 25%. And of course, they add up to 1. Okay, now the distribution, the probability distribution, I'll go ahead and graph that real quick. This is not the way to do it, but I'm doing it like that anyway. I'm trying to get to give me a rectangle. There's one. So I'm just going to move this rectangle into position. Something like that. It's pretty good. Oops, 50% all the way up. Okay. So the next variable, this was variable X. The next variable is called Y. It has the same distribution really, but it's a little narrower. 7 to 9 is a farther distance than from 1 to 2. So same thing here. The values are 1, 2, and 3, and I'll make a total row down here. So same probabilities. There's only 1 out of 4. So I'll just go ahead and put this in real quick. Okay, like that. Total is 1. Okay, so and I think, see if I can just paste those other ones in. These bars are thinner because the distance from one value of the variable to the next is smaller. So I wanted one to be wide and the other to be narrow. So we can see how, when you put the two populations together, how the variability sort of combines. I don't know that I want to go through a lot of trouble to compute the mean. We know the formula, but you can see what the mean is. So let's just use that. So the formula for the mean is the sum of x times p of x. Okay, and same thing for the y. It's the sum of y times p of y, like that. Just a different letter. But you can see the mean. So let's just say, okay, this is going to be 2. sorry, it's going to be 9. And for y, the mean is 2. Okay, so we won't go through a lot of trouble to do that. I do want to get the range. So the range is the max minus the min. So on the first one, the highest value is 11. So you just do max minus min. So it'll be 11 minus 7, which is 4. And on the other one, the range is 3 minus 1, which is 2. Okay, so those are going to be important numbers when we combine these. So I think I'll highlight the 4 is the range and 2 is the other range. The means are 9 and 2. Okay, standard deviation is going to be a little more work. I feel like I have enough space to do it. I'm trying to think. This is something normally we would use calculators that have all this programmed in. And teaching online changes my tools. So I need some space, I guess, to work. But I don't have that. Okay, so I think what I'll do is just add a little thin x squared p of x column. We'll just do it by hand. Easy enough. So on this first one, I'll add a little x squared p of x. Okay, and so we have to do 7 times 0.25, which I think is 3.75. Oh, x squared, my bad. I'm not thinking. So 7 is 49. So what's 7 squared is 49. So what's 49 times 0.25? Anybody? So
You
again,
said 49 times
yeah, because
25.
we're squaring the x, which is 7 squared. So that's 49 times p of x, which is 0.25.
So 12.25.
Good. Okay, now the next x is 9. So when you square that, you get 81 times 0.5. What do you get there?
$40.5.
Right. Okay, and then 11 squared is 121. So 121 times 0.25 is 30.25. Okay, so these are going to add up to what? We're going to add them up 12.25 plus 40.5 plus 30.25. So those add up to 83 even. Okay. So I think we can do the standard deviation now. So
how did you get 30.25 for?
remember, we're doing x squared times p of x. So we did 11 squared here, which is 121. 11 squared is 121 times p of x, which is 0.25. So we just multiply 121 times 0.25.
Oh, yes, I see. Thank you.
No worries. Okay, so here I'm gonna have to squeeze this in, but it's the sum of x squared p of x minus the mean squared. Okay, so this is gonna be the square root. X squared p of x was just 83. Okay, And the mean was 7. So it's minus 7 squared. Sorry, the mean is 9, right? So minus 9 squared. And 9 is 81, right? 9 squared is 81. So it's just 83 minus 81, which is just square root of 2. Okay, which you can write as 1.41 if you like. But the square root of 2 is the standard deviation. So the variance would be the square root of 2 squared, which is what? I know you know this. So if you square square root, it goes away. So the square root of 2 squared is 2. Okay, so that was the part I was hoping not to do by hand. Unfortunately, we've got to do the next one by hand also. So we're going to do the same thing for the y's. Add another column. Okay, so this would be y p of y. Okay. Sorry, y squared p of y. We're doing the standard deviation only because we have the mean. Okay, so here you do 1 squared times the probability 0.25. So this is just 0.25. On this one, the next one, it's 2 squared, which is 4 times 0.5. 4 times a half is 2. So this will be just 2. I'll put a 0.00 to line up the decimals. Okay, the last one is y is 3. So 3 squared is 9. And 9 times 0.25, I think. Anybody know what that is?
2.25.
Good. 2.25. Like that. And now we got to add those up. So I think it's going to be 4.5 when you add it up. Like that. So the standard deviation, the formula, you know, is, we'll do it in terms of y instead of x, but it's the sum of y squared times p of y, which we just did, minus the mean of y squared. Okay, so I just put that little y next to the mean. The other one should have had an x, I guess. Okay, so this would be the square root of the sum of y squared p of y was just 4.5. Okay, minus 2 squared. So that's just 4.5 minus 4, which is the square root of 0.5. So the square root of 0.5, it's like 0.69 or something like that. Uh, 0.707, we'll say. I think 0.71 is fine. But if you square this again, you get your 0.5 back. So the square root of 0.5, if you square that, you just get 0.5. So the variance is 0.5.
How'd you get 0.71?
I did it on my calculator. I just took the square root of 0.5.
How do you enter that into your calculator?
Well, I mean, it depends on the calculator, right? I mean, if I do Desmos, you know, and I'm kind of going to be encouraging you guys to do Desmos for your calculator. So let me get that. I'm going to pull that up real quick. Okay, so here's Desmos. And so let me clear that last thing we did. So if you, again, down at the bottom, there's a little pop-up for a keyboard, but it also has things like square roots. So if you can see where I'm pointing on the screen in
Yes.
Desmos, that's the
Yes.
square root. It looks like a check mark.
Okay.
So just click that and then put in the 0.5. So it's 0.707.
Okay, thank you.
Yeah, Desmos is super cool and it's really good for doing complicated stuff. So it'll get better and better as we go. Where was I gotta go back to the iPad now. Okay, so we got our mean, our standard deviation. Now, we have to do a new population here. So this one's called X plus Y. This is every X plus every Y. Why in the world would you do that? We do. Okay. That's what X plus Y means. So X is a lot of values and Y is a lot of values. So if there's 4 of each, then if you do every X times every Y, that's going to be 16 values again altogether. So I'll go ahead and list these. If you take the 7, that's the first X, and you add all the Y's here. 7 plus 1 is 8, plus 2 is 9. There's another 2, so you get a 9 again. And the 7 plus 3 is a 10. So you would get 7 plus 1 is 8, plus 2 is 9, plus the other 2, another 9, plus the 3 is 10. Okay, the next X value is now 9, okay? And you have to add all the Y values to it. So 9 plus 1 is 10. 9 plus 2 is 11. There's another 2, so you get another 11. And 9 plus 3 is 12. Okay, so that's the first 9. There's another 9 that has to have all the Y's added to it. So you're going to get the same values again as the last row. So you're going to get a 10, 11, 11, and 12. Okay. And then finally, there's an 11, which we have to add all the Y's to. So 11 plus 1 is 12. 11 plus 2 is 13. There's another 13. Then 11 plus 3 is 14. So these are all X plus Y, which is different from what you do in algebra. So you have to kind of get past thinking, you know, X is just a single value. No, it's a lot of values. Okay, and now the mean, it's kind of hard to see, but if I was, let's do this. So if I put X plus Y here and then the probability of X plus Y, the X plus Y's are 8. There's some 9s. There's some 10s, 11, 12, 13, and 14. Okay, those are the X plus Y's that we have. And there's 16 values altogether. Okay, so the probabilities are going to be out of 16. So the 8, there's only one of those out of 16. So I'm going to write it real small, 1 out of 16. The 9, there's 2, so it's 2 out of 16. The 10s, there's 3, so it's 3 out of 16. There's 4 11s, so 4 out of 16. Okay, it goes down from here. Then there's 3 12s. I'm not lined up anymore, so I'll fix that real quick. There's 2 13s, so that's 2 out of 16. And there's 1 14, so that's 1 out of 16. And then real quick, I'm going to approximate these. So 1 out of 16, I don't know, I think it's 0.0625, but let's double check here. Yeah, 0.0625. 2 out of 16 would be twice that, so that's 0.125. 3 out of 16, I think it's 0.1. I don't know what it is. 3 divided by 16 is 0.1875. So I'll say 0.1875. I didn't round that. 4 out of 16 is a quarter, so that's 0.25. And then they go back down, repeating those same values. Okay, so this is sort of a bell-shaped distribution as well, with the highest value in the middle. And I'll go ahead and start making my histogram over here. So 8 just occurred 1 time. So I'm going to try and carefully put that in. Probability 0.0625 way down here. Okay, the 9 occurred with a probability of 0.125. So that's going to be right there, I think. Okay, the 10 had a probability of 1875, so that's almost 20%. Okay, the 11, oops, was 0.25, so that's actually right where it needs to be. And then the rest of this, it just goes down from there. So I'm just copying and pasting my rectangles. Like that. So it's still bell-shaped. I mean, they started off bell-shaped, okay? And one of the rules for combining distributions is if you add the variables for 2 different distributions, if they start off bell-shaped, then the sums will be bell-shaped as well. Differences come out bell-shaped too. Okay. Now, I think you can see the mean here. So real quickly, what's the mean? This is mu, the mean, which is the expected value of the variable, which is called x plus y. So
0.25.
now look at the center of the distribution and tell me what x is there in the middle. Or I should say x plus y is on the graph.
0.25.
Yeah, so
Oh.
the mean's 11 here. Okay. Now the range goes from 8 to 14. Okay. So we just, for the range, we just do 14 minus 8, which is 6. And I want you to notice that the ranges add, even though, well, yeah, the ranges add. So above, the ranges were 4 and 2. Now the range is 6. You got it? Okay, now to get the standard deviation, I'll tell you what, I'm just going to go back to Desmos and remind you how this works in Desmos. So I don't want to do all these by hand. I'm getting a little worn out. So let me pop over to Desmos. And you can put in the probabilities, but you can also just put in the values from the population. So A equals, and I just type all the values in. So they are 8, 9, 9, 10, 10, 10, 4 11th, then, right? Then 3 12s, 2 13s, and a 14. So I'm not using the frequency table or the probability distribution to get the mean, but it's the same population, so it'll have the same mean. Okay, so I just say, what's the mean of A? We already know that it's 11. So that should come up as 11, and it did. The standard deviation is the thing I didn't want to do. Ugh, I wonder if we could do the population standard deviation. That's my problem. That's not going to work. Okay, it looks like it has a command for that. So I put a P after it, standard deviation with a P after is a population standard deviation. That turns out to be 1.5811. We'll put that in for the standard deviation. And then I have to square this. So I have to do the standard deviation of the population A and then square it. So I'm raising it to the second power, and you can see it's 2.5. That's the variance. Okay, so let me go back to the notes. That's a lot easier than doing it in my hand. We could have done the other ones that way too. And we would have gotten the same values.
So when I'm in Desmos for these ones, I have to always add that P for population.
But if you're, yeah, but you won't, don't worry. This is a real theoretical discussion, and the results that we're going to get out of down at the bottom here on the next page are what you need to be able to do at the end. Okay, so right now, don't get hung up on this theoretical discussion. I'm not going to ask you to repeat the theoretical discussion. Okay. So just real quickly, the standard deviation we got was, gotta go back to, I forgot what it was. It was 1.58. So that was like the sigma for the standard deviation is 1.58. The variance is what I needed here. So this is gonna be sigma squared or var of x plus y. Okay, so the variance of x plus y came out to be, when we squared the standard deviation, does anyone remember what it was? It was 2.5. And what I need you to see here is, in the same way, remember the range is a measure of spread. So on the x's, the range, the ranges on x and y were 4 and 2. And when we added the variables, the range was 6. Okay, so the ranges just add. But this doesn't happen with the standard deviations. If you add up the standard deviations, 1.4 plus 0.7 is like 2.1, which is not the standard deviation of the sum. So standard deviations don't add when you add variables, but variances do. So if you notice the variances, 2 and 0.5, when you add the variables, the variance is 2.5. So the variances add. So what we saw here is the expected value of x plus y. That was the 11. Oops, my bad. So that was the 11. Let me highlight that. Which was the expected value of x, 9, plus the expected value of y, 2. So you see how the expected values add? The 11 is the 9 plus the 2. Okay, so we say the expected value of x plus y is the expected value of x plus the expected value of y. Okay, that's an algebraic statement. It's a rule for expected values. The same thing happened with the variances. The variance of x was 2. The variance of y is 0.5. The variance of x plus y is 2.5. They add. Okay, so then I would summarize that by saying var of x plus y was var of x plus var of y. Like that. So we've learned that. Now, this next question is, well, what if you subtract every x minus every y? I'm not going to go into all the details. I'm just going to give you some of the information. So if you take every x and subtract every y, I'm doing the 7, the 9, and the 11, and subtracting the 1, the 2, and the 3. Remember, there's 2 9s and there's 2 2s. So if I do x minus y, it's 7 minus 1, which is 6. 7 minus 2 is 5. There's another 2, so you get another 5. And 7 minus 3 is 4. Okay. Now the next x is 9. 9 minus 1 is 8. 9 minus 2 is 7. 9 minus the other 2 is a 7. And 9 minus 3 is 6. There's another 9. So when you subtract the y's, you get the same values. And then the biggest value of y was, of x was 11. So 11 minus 1 is 10. 11 minus 2 is 9. Another 2 gives another 9. And 11 minus 3 is 8. Okay, so very quickly, if you graph this, you'll see that you get the exact same distribution. Okay, so without going into a lot of detail here, this is exactly the same probability distribution. Let me see if I can get this right. It goes from 4. I have to make it wider, so it's not wide enough. So you want to go ahead and do the distribution again with exactly the same heights on the bars. Okay, so it's the same shape. You can see the 7 occurs 4 times, just like the 11 occurred 4 times. So 7's the mean. So this is the mean. I'll call it mu, but it's the expected value of x minus y. Okay, and that's 7. The range is from 4 to 10 now, so you would do 10 minus 4, and that's 6. Notice it's exactly the same width as before. Whether you add the values, the range is 6, or subtract the values, the range is 6. It has exactly the same distribution shape, so it must have the same width, which means the standard deviation would be the same. The standard deviation will still be sigma equal to 1.58. And when you square that to get the variance, this is sigma squared, which is the variance of x minus y. This also comes out to be 2.5 because they are exactly the same shape. They have the same width. I'm going to just let you guys catch up. Oops. Okay. So here, I want you to see that the means do something similar when you subtract the variables. So with x, the mean was 9. With y, the mean was 2. Okay. The mean of x minus y is 7. So the mean's subtracted when you subtract the variables. But the variance is still added. So notice that the variance of x was 2. The variance of y is 0.5. And whether you add or subtract, the variance of x minus y is still 2.5 because the distribution has the same width. So the variance is added. So I want to get this last statement, expected value of x minus y is the expected value of x minus the expected value of y. So that was the 9 minus 2 for the two means to get 7, which is the mean of x minus y. And then just also, again, because the variances of x and y were 2 and 0.5, we noticed that for the variance of x minus y, that's the same, x minus y is the same width as x plus y. These distributions are identical. They're centered differently. X plus y is centered at the mean of x plus the mean of y. The means were 9 and 2, so the mean of x plus y is 11, where the mean of x minus y is 7. Okay. But the distribution shapes are identical, so they should have the same spread. And in fact, as we see, the variance of x minus y is 2.5. But again, that's the variance of x plus the variance of y, 2 plus 0.5. So even though the variables were subtracted, the variance is added. So you would say var of the difference, x minus y, just as wide as x plus y. So this is the variance of x plus the variance of y. All right, now real quickly, we want to see what happens when we multiply a variable by a value. So just as a reminder, y had the values 1, 2, 2, and 3. So 3y just means we multiply each y by 3. Okay, that's all it means. So 3y looks like, again, the y values are 1, 2, 2, and 3. So when you do 3 times that, you'll go 3, 6, 6, and 9. Like that. Easy enough to graph. So let's do a quick graph. Just a bunch of rectangles as usual. And let's see if I can get this going. Third try is a charm. There it is. Okay, so 3 occurs one time out of 4, which is 25%. Like that. Which is actually the same as the 9. So I'll go ahead and paste that over. Like that maybe. And the 6 occurred at 50%. So let me paste that in. So I'll just grab that bar up to all the way up to 50% like that. Okay, so it's still a bell-shaped distribution. As a matter of fact, all these are bell-shaped. We started with 2 bell-shaped distributions, and when we add the variables, it's bell-shaped. When we subtract the variables, it's bell-shaped. When we multiply every variable by a value, as long as the value is not 0, it's still a bell shape. And you can see the mean is 6 here. So this would be the expected value of 3y is 6, which is 2 times 3. 3 was the mean of y, you may remember up here. Sorry, my bad. The mean of y is 2, okay? And 3y needs to be 3 times 2, still 6. Okay, but this is 3 times the expected value of y. Okay. Standard deviation, we're going to have to go over to Desmos real quick. So let me pop over there. Okay, so we'll have to do that real quick. Okay, so the list, I'll just call it A, is our 3y values, which are 3, 6, 6, and 9. Like that. We already know the mean is 6, but just for the heck of it, mean of A, 6. Okay, now I need the population standard deviation, STDEV with a P for a population standard deviation, slightly different formula of A, 2.121. So I'm going to put that in the notes. I'll just call it sigma. Roughly 2.121. Okay, now the variance is what I need, and that's the standard deviation squared. So if I take the standard deviation of the population, A, and then raise it to the second power, I get 4.5. Okay, so let me just pop back over to my iPad real quick. Okay, so I got my standard deviation here. The variance is sigma squared, okay, which is the variance of 3y. Okay, it turns out that it's 4.5. And then just to kind of go back and remind ourselves what the variance of y is, way back up here, the variance for y was 0.5 down here. Okay, so I want to see how many times 4.5 is bigger than 0.5. And of course, 9 times 5 is 45. So this is 9 times 0.5. Now the 9 comes in because remember I multiplied all the values of y by 3, computed the standard deviation, and then we squared it. So the standard deviation is actually 3 times bigger, but because you've squared it, the variance is 9 times bigger. So this 9 is really a 3 squared times the 0.5, and the 3 squared was the variance of y. Sorry, the 3 squared. And the 3 is the number we multiplied by. The 0.5 is the variance of y. So the principle we get out of this is that the variance of 3y is 3 squared times the variance of y. And now I think we can go ahead and we've got just about everything here in terms of a summary. And I'm just going to kind of point these things out here that when x is a variable, we call mu sub x as the mean or the expected value. It was a bell-shaped distribution, and sigma squared was the variance of x. I put a little x down there to distinguish it from the y. When the variable is y, the mean of y is the expected value of y. Again, it was bell-shaped, okay? And the variance of y is sigma, it's just standard deviation squared, okay? For the variable x plus y, the mean is the expected value, and it's the mean of x plus the mean of y. That is the expected value of x plus the expected value of y. The distribution of x plus y was still bell-shaped, and the variance is added. Okay, variance of x plus y is the variance of x plus the variance of y. Same thing for the variance when you subtract the variables, but not the same thing when you do the expected value. So for the expected value of x minus y, that's the expected value of x minus the expected value of y. That is, when you subtract the variables, the means subtract. Makes sense. The distribution was still bell-shaped, but the variance is again added. So the variance of x minus y was the variance of x plus the variance of y. We saw both of those distributions were identical in shape, but they had different means. So for the sum, the means add, and for the difference, the means subtract. Because the distributions have the same width, the variances have to be the same, and they add. Okay. So you see this rule here, the variance of x minus y is the variance of x plus the variance of y. And the last thing we saw was the expected value of 3y was 3 times the expected value of y. So when we do the expected value of kx, that's k times the expected value of x, still bell-shaped, like when we multiplied by 3, okay? And then the variance of kx is k squared, that should say times the variance of x down here. So we'll fix that. I'll put it in green and just leave it there just so you can see the mistake. And there's a statement here that there's 2 asterisks in this, actually, this asterisk and this asterisk, which is that the variance formulas here assume that the variables x and y are independent. And if they're not independent, technically, those 2 statements are not true. So independent variables, just as a reminder, are variables that do not influence each other. So knowing the value of x doesn't affect what the random outcome of y is. They just don't influence each other. So as long as they're independent, you can count on the variances adding, whether you're adding x and y or subtracting. Okay, so that's it for this section, which is 4.2. So this is section 4.4, which is on binomial experiments. Okay, so a binomial experiment is really common in statistics and research. Binomial experiments are just basically whenever you do categorical data in a statistical study, you're doing a binomial experiment. Okay, so you'll see this occurring a lot as we go through the class. And a lot of you guys are doing categorical data. So in your projects, and so those are, in many cases, those are binomial. So for a binomial experiment, basically you have, this is where you conduct, and I'm writing, okay, good, it's coming up. You conduct n trials independently with 2 outcomes each. So I'll just say each with 2 outcomes. The outcomes are S for success and F for failure. So this could be like tossing a coin. Okay. Now, real quick, there are a bunch of, so that's simple, that's a binomial experiment. Every trial has 2 outcomes. So binomial means 2, right? And that's why we call it a binomial experiment. So N is the number of trials. Okay, S stands, I already wrote it up here. S stands for success. This is not a number, that's an event. Something that happens. F, of course, is failure. Also, failure just is the complement of success. This means not success. Okay, that's the definition of failure in case you didn't know. And then X is going to be the number of successes in N trials. Okay, little p is going to be the probability of success in one trial. So we just write that P of S. Okay. Q is the probability of failure. which is P of F. These are complements. So I don't know if you remember the rule of complements. The probability of rain, let's say, was 30% today. So it's a 70% chance it doesn't rain. So that's 1 minus 0.30 is 0.70. That's the rule of complements for opposite events. Probability of failure is 1 minus the probability of success. And this would be 1 minus P for Q. Right here is Q, and right here is little p. Those aren't capital P's. Okay. And then P of X, this is a capital P of X. This is a probability of X successes. Probability of X successes in trials. Okay, so probably easiest just to do this. So what I'd like to ask you to do is grab 4 coins. I'll give you a sec. I'm going to go grab 4 coins myself. They don't have to be the same. They could be any coins at all, just as long as you can see heads and tails on them. I got my coins, and you're going to shake them and drop them on the table. And then you're going to tell me how many heads you got. So the variable is number of heads. Every trial is dropping 1 coin, and that has a success or a failure, heads or tails. So success is heads this time. Okay. So we want to go ahead and shake these coins, drop them. Okay, I got 1 heads. So for me, I'm going to put a tally mark for 1 heads. And then I just want to go through the list here. Actually, let's do it this way, because some of you did it and maybe some of you didn't. Shake your coins, drop them, and then in the chat, I would like it if you would just write down how many heads you got. Oh, here they come. I'm just going to let them come in and then I'll tally. If it's moving constantly, then it's hard to keep track of. Well, it seems like it's slow. Oop, there's another one. There's another one. 3 out of 4. Okay. Okay, you guys doing great. All right, so I'm going to put in the rest of these. So Seth's got a 1. Matthew's got a 3. Amber has a 2. Megan's got a 2. Usa's got a 1. I don't like these ones. Nan has a 2. Lauren a 2. David's got a 3. Nick's got a 1. Carrie, oh, Caitlin's got a 1. What's with these ones? Okay, Carrie's got a 2. Monica a 2. Why don't we get any 3s? Paul's got a 2. Nahimana's got a 3. Finally, we get a 3. Donnie's got a 1. Selena's got a 2. And Ryan's got a 2. Okay, so what's weird is we didn't get any 1s or 4, or sorry, any 0s or 4s. So let me go ahead and let's do a simulation. This is slowly coming up. This, and it's what you're seeing is all wrong. So I'm going to stop that share and bring it back up. So slow. It wasn't like this last week, but it's been horrible this week. Okay, so now you can, wait, not yet. Okay, now you can see my tallies. So you can add those. And then I want actually to do a whole bunch more, and I'm not going to do that by having you guys toss these. What I'm going to do is show you how you can make a simulation with a 50-50 coin toss. And we're going to do it a whole bunch of times. Okay. So I think I'm going to do it 100 times. Now, right now we have 10, 15, 18. We have 18 people that did it. And I want to get up to 100. Okay, so we're going to make a simulation. So I'm going to open up a Microsoft Excel sheet real quick here, zoom in a bit and share it with you. Okay, so here's my Excel page. So real quick, I will show you how to do a random number in Excel. So you say equals rand. There are no nothing to pass to it, so you give it empty parentheses, which is weird. You hit enter, and it gives always a number between 0 and 1. And I can have it recalculate by pressing, I'm on a Mac, so I do command equals, and you can see it's just randomly giving me a number between 0 and 1. And it gives a what's called a uniform distribution, which means any number, any range of numbers is basically equally probable. So all the outcomes have the same probability with the uniform distribution. Okay, so this is what you get. So half of these are going to be below 0.5 and half will be above 0.5. So I'm going to change this command and put an if in there. And I'm going to say if the random number is less than 0.5, I'm going to consider that tails. Otherwise, it's heads. So let me hit enter. Now this first one came up tails. We'll center that. Now if I hit command equal, it'll recalculate. And you can see I'm pressing it really fast, and sometimes it switches, sometimes it stays the same. Just going back and forth between heads and tails. Okay. So this is just a coin toss simulator. Toss, 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 just like that. I want to toss 4 coins, so I'm going to copy that over to 4 cells like that. So now you can see me drop the coins like that. Okay. So they're just flipping, random numbers being generated, determining which coin toss it is, heads or tails. Now I want to have something that counts these for me. So I'm going to say equals count. I want it to count if it's equal to heads. So I'm going to say if, so I have to give it the range, and I want to count any number that's equal to an H. Okay, just the number of heads. So it recalculates. This time I got 4 tails. So it came up as a 0. I'll recalculate here. We'll reshuffle. Command equals. This time I got 2 heads, 2 tails. So it counts 2 heads right here in the simulation. Do it again. Counts as 3 heads. Now I think I said I want to do this 82 more times. So let me just double check here. Yeah, I want to do this 82 times because we've already done 18. So I'm going to select all this and then make copies of it till I have 82 rows of it. So I'm going to go all the way down to row 82, like that. And now I've done the experiment many, many, many times. You can see all the outcomes here. They'll change every time I type something, they'll change because it recalculates it every time you type something in Excel. But I think I'll do a frequency table. So I'll do a column for X, which is my variable. And then a column for frequency. We'll do the relative frequencies ourselves. So X is going to be 0, 1, 2, 3, or 4. And for frequencies, I'm going to have it do that count if command. I want to count if it's equal to 0 in the first row, count if it's equal to 1 in the second row. So here I say equals count if. I'm going to look at all these numbers and have them count. So let me select the range first. All these numbers. And I want to have it count a number if it's equal to a 0. Like that. Okay, and I hit enter, and it's only counted 6 zeros out of all that. Again, this will keep changing every time I enter something because it just keeps randomizing. But I have to do a tweak to make these references absolute. It's a bit complicated. I'm not going to go into details. There we go. And actually, instead of literally saying 0, I'm going to have it just point to the 0, right? Like that. And now it'll update the reference as I go down. So this is my distribution now. That looks pretty good. And again, see, you can just shuffle this as many times as you want. And every time you do, you're going to get a different outcome. Okay. So just goes and goes. All right, so let's go ahead and just start tallying here. I need to add 6 more. So I have to add 6 zeros. So I'm going to go back to the iPad now. And we'll put in the outcomes of this simulation. We're going to add them to what we already did with real coins. Okay, so like I said, hang on.
Professor, why did you pick 82 as the number of times you flip the coins?
Oh, because what I said was I wanted to get 100 altogether. So we have 18 that we did physically. And if I add in the 82, that'll give me 100. Does that make sense?
Yeah.
Okay. So let me just go ahead and put in what we got. We got 6 zeros. So I'm going to add tally marks. I think I'll do them in blue for the simulated ones. So we got 1, 2, 3, 4, 5, 6. We got 18 ones in the simulation. So I'm going to do 18 tally marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We got 32 twos. So I have to do a bunch of tally marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, for the threes, we got 22 of those. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, I think. And we got 4 fours. 1, 2, 3, 4, like that. And so, like I said, this is all out of 100. Let's see, are you guys seeing what I'm seeing here? Yeah. Okay, so the blues are the simulated coin tosses. The greens are the ones we did. And you can see it just kind of builds up that shape into sort of a bell curve. We got 6 zeros. We got, is that 24? Ones. We got, what did that come out to be? 10, 20, 30, 41. Twos, 25, threes, and 4 fours. So I wanted 100s because the relative frequencies would be super easy. So just kind of zooming in on this, it's 6 out of 100. which is 0.06, and so on. These are estimates of the probabilities. In the end, we want a theoretical distribution of probability for this particular experiment and for all binomial experiments. Just remember, a binomial experiment was where you have a set number of trials. At this point, we've done 100 trials. Sorry, no. The trials were the coin tosses. We did 4 trials for each of the experiments, and we conducted the experiment 100 times. Okay. All right, any questions here? I think what we'll do when we do the mean, I think I'm going to do this from a frequency table. So let me go ahead and I'm going to pop over to Excel here. And let me do my share. Now you don't have to pay too close attention here, but the frequencies are called F. Wait, I gotta save this, so I don't want these to recalculate again. So I'm gonna copy this and paste it with the actual text that we were working on. So I'm gonna just paste the values, not the formulas. Okay, so this won't change anymore as I do my computations. Okay, so frequencies are F, and we had a couple of things we did to do the mean from a frequency table. And I know you guys have done this in your homework, so it shouldn't be a big deal. We had an FX column and then an FX squared column for the standard deviation. So if I just do F times X, that'll be 6 times 0. And then I can copy that formula down to do all the FXs. Okay. Fx squared, this is equal to 6 times 0 squared. Okay, I'll copy those down. And then you need totals from all these. So the sum of the frequencies is the sample size. I'll total that up. Okay, 82, the sum of the, oh, but there's 100. I've got to update my frequencies. This will go real quick. So there, in the end, there were 6 zeros, 24 ones when we added our data. There were 41 twos, 25 threes, and 4 fours. Now there's 100 values here. Okay, and then the sum of Fx is related to the mean. So let me go ahead and do that. Okay. And then the sum of Fx squared. Yeah. Okay, so for the mean, I'm just going to type the formula in, and you've got this in your notes. So don't worry about it. You're not going to do anything like this. I'll do the mean there and the standard deviation next. Okay, so the mean is equal to the sum of Fx, which is the 477, divided by n, which is 100. So if you think about it, it totally makes, that's a mistake. It should have been sum of Fx. I clicked the wrong column. So sum of Fx over n is the formula for the mean that you guys did in your homework. It's 1.97. Mean should really be 2. If you're dropping 2 coins, then on average you would get 2 heads if you drop 4 coins. Okay, then the standard deviation has a more complicated formula. I'm just going to put this in here. It's square root of a bit of a mess. So I do sum of Fx squared minus 1 over n, 1 over 100 is 0.01 times the sum of fx quantity squared, like that. And I have to divide by n minus 1, which is just 99. And I think I have to do another parenthesis. Oops. Looks good. Okay, so that's my standard deviation 0.947. So let's just go back to our notes and we'll put these in. Okay, something's wrong. Hang on. Boy. I have to stop this again. Okay, that's better. Okay, so just to reiterate what we got in Excel, the mean was 1.97. So this is sort of a sample mean because it's not every possible experiment where I toss 4 coins. I just did it 100 times. So this is a sample mean. So I'll call it X bar. It was 1.97. Okay, and then the standard deviation from the mean. This is sample standard deviation also. Okay, so this is S, which came out to be 0.948, we'll say. Okay. Now, a quick graph of the relative frequency histogram comes next. So this is where we're just doing bars. And so the first rectangle has a height of 0.06. Let me just get this is going to get moved into position. So first rectangle going to be round here. Again, the height is 0.06. So tried to make it in between 0 and 0.1 is 0.05. So right here is a 0.05. So I just tried to make it a little higher than that. Like that. And then the next one is 0.24. So I'm just going to copy that and paste it up to the right height. So this 0.25 is right on the line, just go a little below the line. Okay, next one has a height of 0.41, so just a little above 0.4, like that maybe. Okay, next one has a height of 0.25, so it's real close. It is on the line this time, but real close to the last one, something like that. And the last one is 0.04. Oops, did not mean to do that. Okay, here's the last one. Like that. So that's a real nice bell-shaped distribution. So I think obviously the shape is a bell shape. which is the common shape we see in probability distributions. And this is not a theoretical shape. Okay, I'm not saying, oh, usually this happens. It did happen with, real data being randomly drawn, either simulated or from real coin tosses. Okay, the simulation behaves just, I don't know if you noticed, but we started with a bell-shaped distribution with the green. When we filled it out a little bit, but the bell shape was maintained even after we used the random trials from a computer. Okay. So it just wants to be a bell shape. And of course, the more trials you do, the better the bell shape is. All right, any questions? All right, then let's go a little deeper here. We need to do some theoretical development to find, I would like, these are just relative frequencies. Relative frequencies are used to estimate probabilities. So if somebody was to ask me, what's the probability if you toss 4 coins, what's the probability of 2 heads? I'd say it's probably around 41%. That's just based on data that were observed by doing that many times. Okay. If somebody said, well, what's the probability of 3 heads? I'd say, well, it's a lower chance at about 25% chance, very similar to 1 head. Okay. And the probability of just all tails is about 6%. Probability of all heads is 4%. I think those should be the same also, because 4 heads, 4 tails is kind of the same thing, right? So I recognize these are relative frequencies that include some margin for error. They're from sample data, not from a population of all possible tosses of 4 coins. We just did it 100 times, okay? So we want to see what would these have come out to be in theory, okay? So let's see here. In choose X is the first thing we have to cover to do a theoretical development here. It counts the number of ways to get like 2 heads, say. And that's actually important because the number of ways something can happen goes directly to the probability of it. So watch this. In choose X is defined as the number of ways. And by the way, we read this is read N choose X. Okay, so it's the number of ways from N trials to choose X successes. Okay. Now this, again, we'll need to be able to count how many ways something can happen, but let me just show you an example here. It says to compute, let's compute the probability of 2, that is the probability X is 2, is the probability of getting 2 successes, and successes are heads. Okay, so S for success is heads. Okay. F, remember, is fail, and that's tails. Okay, so when it says the probability of getting 2 successes, that's 2 heads and 2 tails. So this means you'd have to get, well, I'll just write it more explicitly here. This is 2 heads and 2 tails. So what's the probability of that? Well, you have to list all the ways you can do it. So let me show you what I mean. You could do 2 heads and 2 tails, just like that. And there you've done it, 2. Okay, but that's not the only way to do it. You could get success, fail, success, fail. That's a head, a tail, a head, a tail. Or you could get a success and a success and a fail. Oh, I did that already. My bad. You could get a success, a fail, and a success. Or how about a fail, success, a fail, and a success? Or can anybody, there's two more. Can anybody see any of the others?
Fail, fail, success, success.
Good, that's one of them. Anybody see the last one?
Fail, success, success, fail.
That's all of them. Okay, so note there are 4 ways. Sorry, there are 6 ways from 4 trials to get 2 successes. Okay. Any questions? So that's what this number of ways from n trials to choose X successes. That thing is going to count, that NCX thing is going to count the number of ways to make this happen. And I said to get 2 successes, I think the better word, just to be consistent, is to choose 2 successes. Okay, now just a quick reminder here that the probability, little p is the probability of success. It's just in parentheses. Little p is the probability of a success, and little q is the probability of a failure. I'm about to use the addition rule repeatedly and the multiplication rule repeatedly. Okay, so just remember, or means add. Let's put a little plus sign there. Or means add, and means multiply. The success, success, fail, fail, those are ands, because I'm saying the first one's a success and the second one's a success, third one's a fail, and the fourth one's a fail. Every time I say and, that's a multiply. Success, the probability is P, fail, the probability is Q. So this is what I mean. You have P, P, Q, Q, 2 successes, 2 failures. Or means add. Success, fail, that's P, Q, P, Q. Or means add. Okay, P, Q, Q, P plus Q, P, Q, P. I always feel silly saying this. Plus, I'm at 2 fails, 2 successes. That's Q, Q, P, P. Plus finally the Q, P, P, Q. All right, and those are all 2 Qs and 2 Ps. So what you really want to do is step back and maybe give yourself some space and say that there are 6 of them. Okay. There's a P to the second. And there's a Q to the second. And we need to understand what all these are, what all these numbers represent. So the 6 is 4 choose 2. So 4 choose 2. Let me do it this way. I'm going to move it closer. Okay, so the 4 choose 2 is 6. What is 4 choose 2? From 4 trials, how many ways are there to choose 2 successes? Let me go to the highlighter. So there are 6 ways from 4 trials to choose 2 successes. That's just the definition of 4 choose 2. And you get 6 when you do that. Okay. The P is the probability of success. So little p here is the probability of a success. Okay, right there. And why is it raised to the second power? Well, because we need 2 successes, right? So 2 is x, the number of successes. Okay, now Q needs to be here because we have 2 failures and that's just part of the problem. So Q is the probability of a failure. Okay. And why is Q raised to the second power? Well, if you're going to have 2 successes in 4 trials, 4 minus 2 is 2, which is the number of successes. So 2 is 4 minus 2. This will be n minus x in trials, x successes. This is the number of failures. Okay, again, the n was the number of trials. Okay. So the 4 choose 2 is n choose x, by the way. So if I did a little ncx, n is the number of trials, which is 4 trials, 4 coins per toss. And we're counting 2 successes right now because that's what the problem asked for. X is 2. So the formula, if you just look at all this, you have to do ncx in front. That's the 6 here. Okay, that's the ncx. And then p to the x. X being the number of successes, you want x of those, and little p is the probability of success. And then if you're going to have x successes, then there has to be n minus x failures. N is the number of trials. You subtract the number of successes and you get the number of failures. And Q is the probability of a failure. Okay, so that's the formula for the probability distribution. NCX is the only tricky part. When we learned that 4 choose 2, let me highlight here. We learned that 4 choose 2 is 6. That is to say, from 4 trials, how many ways are there to get 2 successes? The answer was 6. How did we get that? By listing all 6 ways. Okay, that's a lot of work, and you can't just list them every time. So what we're going to have to do is use a formula for getting this. Now, you're going to need to know what a factorial is. I'll explain. Okay. So n choose x, the formula uses factorials. In the numerator, you have the number of trials, factorial. I'll explain. In the denominator, you have the number of successes with a factorial. That's an exclamation point. Then in the denominator, you have the number of failures, which is n minus the number of successes. Again, a factorial. Okay, so when we write n with an exclamation, we read this n factorial. Okay, and it means n times n minus 1 times n minus 2, etc., down till you get to 3, 2, 1. So for example, if you do 4 factorial, this is just 4 times 3 times 2 times 1. You just count down to 1 and you multiply. So 4 times 3 is 12, times 2 is 24, times 1 is 24. That's 4 factorial. Now, when they ask us to do 4 choose 2 using the formula above, let's see what we come up with. 4 choose 2. Okay, in the numerator, you do the number of trials, factorial. That's 4 trials. Okay. down below, you do the number of successes. There were 2 successes. Okay. And then also the number of failures. 4 minus 2 is the number of failures. So that's 2 factorial. Okay. So 4 factorial, we already did, was 4 times 3 times 2 times 1 over 2 times 1 times, that's 2 factorial. Another 2 factorial is 2 times 1, and you can cancel some stuff. In the end, it's 24 over 4, which reduces to 6. There are 6 ways. We knew this, right? That's the 6 that I've been talking about up above when we counted the number of ways. There were 6 ways. Okay, so you can count them by just listing out all the ways to get 2 successes in 4 trials. Or you can use a formula that counts the number of ways for you. Okay. Just a quick, I'll show you how to do this in Desmos. Oh gosh, how are we doing here? Just 4 minutes left. I think, so for our coin tossing experiment, we need to know what all these variables are. So little p is the probability of success. Let's assume that the coins that we were tossing are fair coins. So the probability of a success is the probability of getting heads on one of your fair coins. What's the probability of that? Anybody? All right, then, the probability of heads is 50%, 0.50. Probability of tails is always, the definition of Q is 1 minus P, okay, which is the probability of tails. Okay, so let me just denote this in case you've forgotten. Little p is the probability of a success in one trial. Little q is the probability of a failure in one trial. So that's P of F, I'd say. Okay, so if success has a 50% chance, then failure also has a 50% chance. That's the rule of complements. Okay, they have to add up to 1. Now, it says use the formula to evaluate P of 2. So I'm going to copy the formula down from up above. So, and I'm going to write maybe small P of 2. That's the probability X equals 2. So I'll go ahead and write it like that. Okay, so the formula is N choose X, P to the X, Q to the N minus X. And as a reminder, N is the number of trials. We were tossing 4 coins, so N is 4. Okay, we did it many times, but each time there were 4 possible outcomes when you drop the 4 coins. Sorry, there were 4 trials by dropping 4 coins. That's what I meant to say. So N is the number of trials. Okay, so little N choose X is 4 choose 2. Okay, P is 0.5, so I'll do 0 times 0.5 to the X, that's the second. Q is 0.5. This is to the N minus X, 4 minus 2. So there's 4 trials. If you take out the 2 successes, you get the number of failures. Okay, now we already determined 4 choose 2 is 6. 0.5 to the second is whatever it is. So I'll just leave that as times 0.5 to the second, and then times another 0.5 to the second. So that's actually 0.5 to the fourth if you want to do it that way. Half a moment. Okay. So I'm going to pop over to Desmos. We're going to do a handful of things in Desmos today, so I'll show you that. So here's Desmos. So I have to do just 6 times, and then it was 0.5. You can just raise it to the 4th. The exponent key, you do shift, and above the 6 is the exponent. The caret is what they call it. So shift 6 raises an exponent. There's really 4 factors of 0.5 all multiplied together. So it's 0.375 here. So this says, in theory, this is a 37.5% chance of getting 2 heads when you drop 4 coins. Okay, I'm going to zip back over to my iPad real quick. Okay, so what I've done is I've put in the answer to this right here. So the theoretical probability is 37.5%. So we predict that if you do this, for thousands of trials, maybe that just almost exactly 37.5% of the trials will yield 2 heads out of the 4 coins. Okay, 37.5% is therefore the probability. And I just want you to see what happened with our random trials, only 100 trials. It's supposed to be 37.5%. We got 41%, which is pretty close. I've seen better. Sometimes it comes out at 37, 38%. This time we got 41% with 2 heads. So that relative frequency is pretty close to the theoretical probability of about 38%. Any questions about that? So just remember the law of large numbers. These relative frequencies here approach true probabilities with large sample sizes. And just to kind of give a sense of it, usually when you do a sample of 1,000, you get 3 percentage point error. And here, the real probability is 38%-ish. We got 41%, and that's within a 3-point margin of error. And only from 100 trials. Normally you have to go up to 1,000 to get an error that small. So that's pretty good. Now, I have to step aside and do a little theory here. First of all, any questions?
Yeah. How soon are you going to upload chapter 4 notes and lecture online?
When they're done. So I only upload when they're done.
So that
So
would be
that should happen. That should happen today or tomorrow. Yeah.
thanks.
Yep, no problem. Okay, so developing a formula for the mean and the standard deviation. So you can see that we did practical mean and standard deviation here, treating all these 100 trials as a sample of trials. We were trying to average the number of successes on average, just using, I don't remember how I did it, but one way or another, I figured out the mean to be about 2, just a little less, and the standard deviation to be about 1, again, just a little less. Okay, but those are sample mean and sample standard deviation, which would be different for the mean of, an infinite number of of times that the experiment is run. What's the average number of heads that you would get when you drop 4 coins? We're estimating at about 2 heads with a standard deviation of 1, but that's a sort of based on relative frequencies. What we really want is a theoretical mean and standard deviation because that'll be more accurate in the long run. Okay, so what we have to do is kind of simplify the problem a little bit. Let me go ahead and read. It says, let's develop a formula for the mean and standard deviation of the variable x in the binomial experiment. First, we have to consider a very simple case where we're doing an experiment with just 1 trial. Okay, so this is a theoretical development. You wouldn't be asked to do this on an exam. So let's X represent the number of successes. Again, there's just one trial here. So that means N is 1. Okay. That's how many coins you're dropping. Okay. So if you drop 1 coin, you're either going to get 0 heads or 1 head. Okay. And don't forget, little p is the probability of success in one trial. Okay. So if you get 0 heads here, that means you had a tail, which is a failure. And the probability of failure is Q. So we would put a Q down here for the probability of 0 successes. Okay. Now the probability of 1 success means in the 1 coin that you dropped, you got a success. And the definition of a probability of a success in one trial is little p. Okay, so let me put down here. Little p is probability of success. Little q is the probability of a failure, which is 1 minus p. Okay. Q plus p, remember those by the rule of complements, those add up to 1. So we know that the total here will be 1. And down below on this next page, just to remind you, the formula for the mean is the sum of x times p of x. That's a big P for probability of x successes. Okay, so looks like I'm using a capital X for this very simplified version with 1 trial. So I'm going to change these X's to capital X just for right now. Okay. And so it says multiply x times p of x. So I better add that x times p of x. And then we would multiply that. So 0 times q is 0. And 1 times p is p. So those two guys add up to just p. And so what this is that's the sum of x times p of x, which is by definition the mean. So if I go to this next page, the sum of x times p of x was p. That's the mean. So the mean is the probability. When there's only 1 trial, the mean is the probability of a success. Which is just little p. Now, we also have to do the standard deviation. So let's see if we can remember the formula for the standard deviation. So sigma, it says standard deviations always have a square root. I'll do that last. So the formula for the standard deviation in any probability distribution is the sum of x squared, p of x, and then we subtract the mean squared. So minus the mean squared. And then all of that goes inside the square root. So generally we'll need a table added, or sorry, a column added to the table called x squared p of x. So this looks pretty simple. 0 squared times q. On the first row here, x squared is 0 times p of x, that's q. So 0 times anything is 0. We'll just put a 0 there. Oops. And then 1 squared times p in the next row is just 1 times p, which is p. So that looks the same. Okay, and 0 plus p, again, this adds up to p. Okay, now standard deviation, you got to plug this all into a really ugly formula. So here we're going to try and write small-ish. Oh, so the square root of the sum of x squared times p of x, that was just p. Okay, and then minus mu squared. Well, the mean is up above. That's p as well. We have to subtract p squared. Okay. And then this factor, so you have the square root of p times what? Can't, waiting for help here. Might have to start calling names pretty soon. Caitlin, I see you. Thank you.
No, it's 1 minus p.
What is it? Sorry.
Is it 1 minus p?
Yeah, and since I got you, do you remember what 1 minus p is? Up
I
here? Anybody remember what 1 minus p is?
Is Q.
And that's q. So this is the square root of p times q. So that's interesting. Now, so the standard deviation is the square root of pq. The variance is the standard deviation squared. So var of x is sigma squared. Okay, so this would be just taking the square root away. So it's the square root of pq squared, like that. So that's just pq. Like that. Okay, any questions there? Just gonna move this over and make sure we see the notation again. I'm sorry about this. The mean is also called expected value, which is E of X. Okay, that's an alternate notation for the mean.
Can you please define expected value again?
It's the mean. And the mean is just the average. So if you go back up to the problem we're doing here, you can see it on the graph. The mean is about 2. Okay, and when we did the computation, now this is based on sample data. We only did the experiment 100 times, but out of the 100 times that we ran the experiment, the average was almost exactly 2 heads out of the 4 trials. And so if someone says, well, how many heads do you expect when you drop 4 coins? You would give the expected value. I expect on average 2. Okay, any questions about that? Does that make sense?
Yes, it does. Thank you.
Standard deviation is just saying how far you expect to not get 2 every time. In general, we deviate from the mean pretty routinely. So this is the average deviation, about 1. Okay, so let's go a little further. So what I have here is a mean and a standard deviation. And by the way, I need to use a capital X because this was when there's only 1 coin being dropped. Okay, we have a mean and a standard deviation from the mean. Okay, that's with 1 coin. Now, here's the thing. We have some properties from 4.2, and I'm going to zip back to those real quick. Right here. Okay, we have a property that says if you look at the mean of the sum of 2 variables, that's the sum of the means. So when this says expected value of X plus Y, that's the expected value of the first one plus the expected value of the second one. We're going to use that to do the mean for when you do a bunch of trials. Okay, so the idea here is, let me just read this because I don't think I'm going to be able to say it better than how I wrote it. When there are n trials, and again, this is from 1 trial, okay? When there are n trials, we can think of this as conducting experiments with 1 trial each. So the total number of successes, that's little x, is the sum of the successes in the individual trials, okay? So Little x is going to be the sum of the successes in individual trials. So what we want to do is figure out what the mean would be for all of the trials when there are n trials. Okay, so the mean is expected value of little x, but little x is the sum of the number of heads in all the individual trials. So big X is either, remember, big X is either a 0 or a 1 here. So you're adding up 0 or 1 depending on whether it got heads or not. And if you just add those up, you would have the value of the total number of heads, which is little x. The expected value of the sum of the number of heads goes back to this rule about expected values here. The expected value of a sum is the sum of the individual expected values right here. Okay, so I would go back down and say, oh, well, this is an expected value of a sum here. That should be the sum of the individual expected values. So the sum of the expected values, which are E of X, that's a capital X, which is the sum for each individual trial. The expected value is just P up here. Excuse me. Right here, the individual expected values are P. So you're adding up P once for each trial. And there are n trials. So if you add P to itself n times, you get n times P, like that. So that's the mean if you do n trials. We'll see if that makes sense in a minute. Trying to figure out where it has this computing the mean here. Oh yeah, there it is. Okay, so we have the mean. We need to do the variance next, mostly because we'll need the standard deviation after that. Okay, so if you go back to variances, variances do the same thing as means. So if you go back up a couple of pages here to this statement with the asterisk, it says the variance of x plus y is the variance of x plus the variance of y. So if you add two variables together, the variances add. And that's what we're going to do down here. So the variant, now again, little x is the total number of heads in the individual trials. So you just add those up for each trial. And so little x is the variant, is the sum of big X. So when you do the variance of little x, that's the variance of the sum of big X, the number of successes in each trial, which is equal to, again, the variance of a sum is the sum of the variances. So we would do the sum of the variance of big X, and that's the sum of the variance of big X, which we determined right here is just P times Q. So we're adding up P times Q for each trial. And there are n trials. So you would have n PQs added together. Like that. And as you know, variance is the square of standard deviation. So standard deviation is the square root of variance. Okay, so this is a pretty theoretical discussion. And the mean and standard deviation are based on probability and theory that we've put together. I wonder if the theory actually works. That's the question. That's what proves theory. Does mathematical and statistical theory work? Well, the theoretical mean, or the expected value for the number of heads, the formula just says up here that it's just n times p. So NP, n is the number of trials. Every time you did it, there were 4 coins, okay? So there were 4 trials, okay? the the probability of success is little p. And we've already defined little p somewhere here to be 0.5 right here. And Q, just while we're looking at it, Q is also 0.5. Okay, so we would just do 4 times P, which is 0.5. Of course, this is 2. Any questions about that? That's just so, we have that computation. We'll talk about how it compares to what actually happened. Okay, is there any question about the computation? Again, the theoretical development is not important. It's important because obviously that's where the formulas come from. I'm not going to make you do that on a test, though. Okay, then the standard deviation is the square root of NPQ we've determined from theory. All right, so this would be the square root. Again, there are 4 trials, 4 coins. So N is 4, P is 0.5, and we already discussed Q is 1 minus P, so that's also 0.5. So anybody, what's 4 times a half times a half?
1.
Okay, so this is the square root of 1, which is 1. So the standard deviation is 1, the mean is 2. Okay, does that line up with the reality of what actually happened? Again, we call it the expected value. We expect the mean to be 2 and the standard deviation to be 1. Got it? And if you go back to the actual trials that we did at the beginning last time, the mean from the sample of trials, almost 2. Okay. And I expect the longer we go with this, the closer that we get to 2. Again, the standard deviations we expect to be 1. It's almost 1. Okay, and again, I expect it to get closer to 1 as I increase the number of times I run the experiment. Okay, so somehow this theoretical discussion about what will happen. And you have to think about this. I mean, we actually conducted the experiment. This discussion, this theoretical discussion, is about predicting what will happen in the long run. And this discussion has told me, yeah, in the long run, I should get 2 heads on average, and 1 should be the standard deviation. Without conducting any trials, we know what will happen. So that's kind of the power and the most important idea behind probability is we don't know what happens in an individual trial. So we can never predict what an individual will do, right? But we can always have this theoretical discussion about likelihoods and talk about the law of large numbers that says, look, we don't know what happens in the short run, but in the long run, reality should fit to this probability model that we've created. Okay, so I want to go ahead and fill out all the theoretical probabilities. Remember, X is the number of heads. We did 4 trials, so you could get, you could get 0, 1, 2, 3, or 4 heads like that. We did the probability of 2. I think it was 0.375 here. So I'm highlighting this one right here. So we've already done the probability of 2. So we can put that in. Like that. Okay. I think I want to compute one more by hand before we have Desmos do all this. So let's do the probability that X is 3 by hand. So just as a reminder, the probability of X is, the formula is N choose X, P to the X, Q to the N minus X. Okay, that's one formula that we developed. And we also determined that n choose x is computed with factorials, but factorials get huge fast. So we're going to need a better tool than just doing it by hand, which is what I'm about to do. N factorial, that's the number of trials. X factorial, the number of successes. N minus x factorial, the number of failures. Just like that. That's the formula. Okay, but over on the right, let's do the probability that x is 3. Okay, so this should be, again, let's line things up here. N is 4. Little p is 0.5. And little q is 0.5. Okay, so the formula just says n choose x. So n is 4. This should be 4 choose 3. And then p to the x, that would be p to the third. And q to the n minus x, that's q to the 4 minus 3. Like that. And maybe over on the left side, let's do 4 choose 3 by hand again. So just to practice it. So 4 choose 3, you have a 4 factorial number of trials over number of successes factorial, that's 3 factorial. And the number, if there's 3 successes, then there's 1 failure. So you do 4 minus 3, which I'll just write as 1 factorial here. And again, as a reminder, 4 factorial is 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. And then 1 factorial, of course, is 1. And you see the cancellation. No point in multiplying this out. 3, 2, 1, 3, 2, 1. You just have 4 over 1, which is 4. Now, this actually makes sense, believe it or not. We're saying 4 choose 3 is asking how many ways are there to get 3 successes in 4 trials. 3 successes is 3 heads. If you get 3 heads, that's 1 tail. So if there's just 1 tail on the 4 coins, then it's either the first coin, the second, the third, or the 4th coin. That's 4 ways to get 1 tail. That's why 4 choose 3 is 4. Okay, so that's a logical thing. How many ways are to get 1 tail? There's 4 ways. Okay, now going to the other side, we can start filling in some of these numbers here. 4 choose 3 we just worked out is 4. P and Q are the same number, so you have a 0.5 to the third times Q, which is 0.5 to the first. And then I would pop over to Desmos. So I'm not going to share this yet. And just do 4 times 0.5 to the third and another 0.5 altogether. That's 0.5 to the fourth. I hold shift 6 to get a raised exponent. And I'm just doing 0.5 to the fourth right now, which is, well, I think I'll wait till somebody else says it. Anybody know what this is?
Yeah, it's 0.25.
Good. So this is 0.25. Okay, so we put that down for probability of 3. There's no rounding here, so I'm not too worried about a rounding rule. If we were rounding, I'd remind you what the rounding rule is for percentages and probabilities. Okay, I'll remind you anyway, it's 3 significant figures. You don't count the leading zeros. But again, I don't fuss about rounding rules when you're not rounding. Okay, any questions? Okay, so we have others to do here. So what I really want to do is show you how to do this in Desmos. Okay, so I think I'll show you, I'll write down some stuff very formally down below, but I'm gonna pop over to Desmos real quick here and delete what I've done so far. And you gotta just type what I type almost identically, and you'll be able to get the same thing as me. I clicked the wrong thing. Hang on. Wrong one. Okay, that's the one. Okay, let's just put values in. Now, the only thing about Desmos, it's really weird, and there's nothing I can do about it. This is the only quirk that I regret from Desmos is that you can't use you can't store values into a lowercase x variable because x has to actually literally vary. It's a graphing variable. So you can't say x is 5. It'll try and graph that. I mean, I'll do it. X equals 5. I don't know if you can see, but that's a vertical line where x is 5. It lets you do all values. The second you say x equals, it thinks it's a graph. So you can't use a lowercase x. You have to use a capital X. So for x equals 2, use a capital X equals 2. Okay, and then just hit enter. And that's fine. Okay, it needs to know n, so just do the rest of this will be lowercase. So little n is equal to 4. There's 4 trials. Okay, I'll go ahead and do p as 0.5. Okay, I think we can type q as 1 minus p. Let's see what happens. Q equals 1 minus p and hit enter. Yep, now it knows what q is. And the point of this, the most important part of this is you can change these. So you can make p 0.7 and then q automatically updates to 0.3. It's sort of like a spreadsheet program where all these are tied together. Okay. So updating p automatically will update q if it depends on p. I'm going to change p back to a 0.5 again. Okay. Any questions? The only thing that's left is starting the computations. I want you to see how Desmos will do the n choose x first. So if you just type a little n, a big C, and unfortunately, I don't think you can use X. Let me just try this real quick. Yeah, it won't do that. So the Desmos thinks the command is NCR. Okay, so you have to type NCR and then do little n comma capital X like that. So remember, n is 4, capital X is 2. And I don't know if you remember, but we counted the number of ways from 4 trials to get 2 successes, and there were 6 ways. And so you can see it comes out as a 6 here. Okay. Any questions about that? Again, it has to be a capital X. And the command, I don't think you can use the lowercase c here. I'm going to see. No, you can't use the lowercase c. It has to be a capital C. Just like we do in our notes. And again, it comes out as a 6. Now, I want to go ahead and do the, let's go ahead and hit enter, that's fine. It'll show you what the NCX is. Now, let's do the whole computation. N, capital C, lowercase r for the n choose x. Tell it the n is little n and the x is big X. So again, it says 6 there. And then type I guess a times, which is an asterisk, and it's p to the x, so type a p. And then the superscript is a shift. And if you hit 6, it'll give a raised superscript. Now, if you can't do that because you're using a phone or something, you could, but it's a little bit of a hassle. There's a pull-up menu here that I'm hovering over. If you pull up that menu, the exponent button is here. Okay, so I'm going to click on that and it gives that raised superscript. So p to the second is what I want. But don't do p to the second, do p to the capital X. Okay. And then you have to press the right arrow to hop out of the exponent. and then asterisk for times again. And now we want to do q to the n minus x. So a q, and then another exponent. Again, you can do a shift 6 or click on the A to the B button in the toolbar. And then this has to be little n minus big X. And here's a mistake. Okay, so I don't know if you noticed, I'm going to show you real quick. If you do little n and then press minus, it hops out of the exponent. So how are we going to fix that? Delete the little n in the exponent and use parentheses. Open parenthesis, little n minus big X, close the parentheses, and there's the 0.375. Okay, that was the probability for getting 2 successes. Now, again, the cool thing about this, they even give you a slider here. You can slide this up to 3 successes, and you can see it changed to 0.25 down here. You can slide this up to, oh, that's not 3 successes. Goodness sakes, that's confusing. I want 3 success, but easier just to type it. So if I change it to 3 successes, down at the bottom, you should see 0.25. And that's one we just did with 3 successes. So you just change the number for X and it will update. Selena, I would like to direct you to the syllabus on your question. Okay, so there you have that. Okay, now again, you can just change these all you like. You could do X equals 1. Now, I actually want to do that at this point. So if I stop my share, I'm going to go back to my iPad.
Are we not finding the answers for 0, 1, and 4? Right
Oh,
here?
yeah, we are, but I'm going to have you guys do it. So I don't want you to see me doing it this time. Okay, so hang on. Okay, so did anybody get, if you can just change X to 0, anybody have an answer for that?
Point 0.0625.
0.625, that's great, thank you. Now change to a 1 and tell me what you get. Someone else.
0.25.
Okay, now that makes sense if you think about it, and you can see the symmetry here. The probability of 1 heads is the same as 3 heads because 3 heads is 1 tails. So 1 tails and 1 heads have the same probability. There's that symmetry that we expect in a probability distribution. Doesn't always happen, but we like to see it for sure. And could somebody tell me 4 heads? So I suspect this would be the same as 0 heads because 4 heads is 0 tails. Could somebody verify 4 heads? Somebody, please.
Point 0.0625.
Thank you very much. Okay, so there we go. Now, you could just kind of look at the probabilities point. Let's look at the probability of 0 here. For 0 heads, should be a 0.0625. Now, when you look at when we actually conducted the experiment, 6% is what we got for the relative frequency. 6% of the trials got 0 heads out of 4 coins. Okay. Did I say 0? Yeah, 6% of the trials got 0 heads. Now this predicts 4%, not predicts, we actually got 4% with 4 heads. This theory here predicts same outcome, 6%. So in the long run, we'd expect that 4% to change if we did it more and go closer to 6% as well, unless the coins are biased, which I kind of doubt. Okay. And the other probabilities line up pretty well as well. If you look at one head, what actually happened was we got 24% of the experiments came out with one head out of 4 coins. 24% was what actually happened. The probability predicts 25% of the time. Pretty darn close. Okay, well within a very small margin for error. Okay, and so the point is, by developing a solid theory, we can predict what happens in the long run, not the short run. Okay, that the law of large numbers is really what this class is all about, our ability to predict things in the long run. But you need a good theory to do that. We're going to go ahead and make our histogram real quick. This first one should go up to 0.25. Oh, no, it's first one was 0.0625. My bad. Right about here, I guess. Oh, I moved it. Okay, looks pretty good. Does anybody have any questions about all that? And again, this is all just to show you how good theory can predict reality. Here's reality. Here's theory. Okay, so they are a very close match. I should say the probabilities are very close to what actually happened with the coin tosses. Okay, is there any question about that? I think I might add, same with the mean and standard deviation. The mean came out 2, as we'd expect, the expected value. All right, now, the next part is just a bigger, I want you to see how this works in polling. So I just have a simple little problem here, but these come back when we start studying polling, basically. So just want you to see how this fits in the larger theory of working with categorical variables like successes and failures, or approvals or non-approvals of a candidate. Okay, so this question says if a president has a 43% approval rating, what's the probability she would get 4 approvals in 10 voters? Okay. So let's just kind of identify all the variables here. So little n is the number of trials. Remember, the trials have 2 outcomes each. How many trials are there in this experiment? Let me go ahead and write this down. This is number of trials. So how many trials do we have with 2 outcomes each?
Is it 20?
How many voters are here?
10?
Yeah, so that they're each voter is going to go one of 2 ways. They're either going to approve or they're not, right?
Right.
Those are your trials, 10 trials altogether. Okay, now x, little x, is the number of successes. So how many successes are they asking for here?
4.
Yeah, 4 approvals. Now it's going to get a little more theoretical. Little p is the probability of success in 1 trial. And you just need to remember, probability is the same as a population proportion. So if I ask you for the probability, and it's in a sort of an applied problem like that, you should tell me the proportion. So what's the probability of getting success in 1 trial here? That would be an approval from one of your participants. It's like a coin toss, but this is a biased coin. What's the probability of a success this time? What do you think? Is it 50%? You think 50% of the voters are going to say, yes, I approve? What's it say here?
Is it 43?
Yeah. If the proportion is 43%, then it's a probability of 43%. If you're randomly, remember, this is a random sample. So if you're randomly selecting people, you got a 43% chance every time you do it. And of course, we assume you're selecting with replacement. Okay, so that's our little p, 43%. Little q is 1 minus p. So this is the non-approval rating. You would do 1 minus the 43%, and what do you get there? 57% of the people are not approving of this candidate. Okay, any questions? Let's do the NCR in Desmos. So let's just do 10, well, 10, let's NCX in Desmos is NCR, and then you put in your value for N and the value for X. Okay. So we're doing 10, choose 4, right? So we can do that. We'll figure that out in a second. So the probability of X successes is N choose X, little p to the X, little q to the N minus X, like that. I'm going to put values in before we start evaluating. So N choose X means 10 choose 4. P is, I think I'd just leave this as a P to the 4, X is 4. And little q goes in with the n minus X. So this will be 10 minus 4. Okay. So that's the computation. Seems a little silly to do this all by hand. You can. But if I pop over to Desmos here, let me see if I can find it again. And of course, I still have all these numbers queued in. So I just need to change this to match the current situation. So I think I'll start by updating n. N should be 10. So I'll just delete what's there and put a 10 in. X needs to be 4. So I'm going to delete 1 and make it 4. So now it's going to be a 10 choose 4. P needs to be 0.43. So I'm going to change the 0.5 to a 4.3 there. And you can see Q automatically updates to 0.57. Also, the N choose X is 210. And we've got a final answer down here. Okay, does anybody have any questions about that? So you can quickly zip through your homework if you make one of these. And you can save Desmos pages, by the way. So if that helps you to remember, I think you might have to create an account, but another thing you can do is if you just do a share, like right now, I don't know if you can see, I'm pointing at the share graph icon and you click on that. It makes a link for you and you can click copy. And this works even if you're not logged into an account. And so if I was to send this to you guys in the chat, you'd be able to click on this, or you could send it to yourself in an email or whatever. So I'm going to post this to everyone, send this to you, and you can save that link. You can save that link, have fun, and click on it anytime you want to do a binomial experiment. Okay. Let's just, any questions about that? So feel free to copy and save that link. The page is already made for you. You can use it if you want. I'd say make sure you can do 1 or 2 by hand, but I'm not going to make you do it by hand on the exam. I may ask you to show your work, but mostly I'd say what's P, what's Q, stuff like that. You know, what's 10 choose 4, you know. Anyway, do you remember what? Let me go back. Come on. Okay, so you may remember what 10 choose 4 was from the Desmos page?
210.
Thank you. Okay, so this comes out to 210. Little p was 0.5, nope, 0.43. So this was to the 4th. Little q was 0.57. That's to the 10 minus 4, so that'll be 6. And again, Desmos has done this already, so I'm not going to do it again. It came out to 0.246. Now I am rounding this. So the rule for, the rule for rounding probabilities and percentages is 3 significant figures. Again, you don't count the leading zeros in the front when you count significant figures. Okay, any questions?
I don't think 10 C4 would be 210.
Really?
Can you just double check, please?
I could, so I'm going to double check it by hand.
Yeah.
So 10 choose 4 would have a 10 factorial on top, a 4 factorial below, and the number of failures, if there's 4 successes, there are 6 failures like that. And then I would do 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And then a 4 factorial, 4, 3, 2, 1. 6 factorial, 6, 5, 4, 3, 2, 1, like that. And then the 6 factorial cancels the 6 factorial on top. It's a little dicey here. I'd say 4 goes into 8 twice. This 2 here would cancel that 2. And 3 goes into 9 3 times. 10 times 3 is 30. Times the 7. What's that?
Yeah, that's right. My bad.
210. So yeah, you can do these by hand. Notice I didn't compute out the factorial. Those numbers get huge. Let me show you what 10 factorial is. So just if I do, I'm going to go, I'm going to be sorry I did this, but I'm going to go back to Desmos here. You should be seeing that. And just to show you what a factorial will do, if you do 10 factorial, that's 3,628,000, which is not a problem. It's a big number, but it doesn't really matter. But if you do 20 factorial, it's going to go into scientific notation. It's 2.4329 times 10 to the 18th, which means that that decimal actually moves 18 places to the right. And everything after this last digit that's a 2 here got lopped off. So they've rounded the number. So the problem with factorials on a machine like this is that they get so big that it ends up rounding it wildly because you do the software just won't hold that many places. So doing factorials in general, we just don't. It's better if you look at how I did it by hand. I just wrote out what 10 factorial was and I canceled everything. So in the end, I didn't have to work with a big number. So that's how you compute factorials by hand. And what the software does is it gets around, it basically does the same thing. It keeps the number small by just saying, well, what do I have to multiply after everything's canceled? And so the software actually won't use factorials either. Factorials are in the formula, but the evaluation is all about not using the factorials. Okay, so let me, there's just a little bit more to do here and we can take our break. Okay, almost back. Wrong one. Okay. So I think I'll squeeze this off to the side. Put it down at the bottom there. Okay, and then it's asking for the mean and the standard deviation for the number. And again, you're doing an approval rating from 10 voters. So I'll just remind you the formulas for the mean. Mu is the mean or the expected value. E of X. The expected number of successes is the formula NP. So we did that way back here. Okay, and while I'm at it, the standard deviation is the square root of NPQ. Okay, so I'll grab those for this next bit. Mu is NP, N was 10. P was the probability of success, which is 0.43. So 10 times 0.43. What's that? Did you leave?
4.3.
Yeah, 4.3. Harder is the standard deviation. So sigma is the square root of NPQ. Okay, which is square root of 10 times 0.43 times 0.57, like that. And I don't know, maybe it's easier to do that in Desmos. I'm gonna pop over there one more time. I hate to say it. It's always a hassle coming back, but I'm gonna delete some of this nonsense here and then just put down mu. I wonder if it has Greek letters. No Greek letters. I thought there were. Oh, well, I just do n times p. So for the mean, it's n times p, and you can see the 4.3 there. Square root has a little button on the toolbar. So it looks like a check mark, but that's a square root symbol. And we'll just do n times p times q. And there it is, 1.57 maybe. So back in the notes, I'm putting mu is 4.3. I actually already did that, and the standard deviation is 1.57. 1.57. Any questions about Desmos? Again, it assumes you have the Desmos needs to know what to do this computation. It needs to know what n, p, and q are. So I have those defined up above here, but you can change them, right? If I make n 100. Then you slide down to the bottom and all of a sudden the mean is now 43, not 4.3. And everything just updates. This is all. Okay. Anyway, I'll see you guys. Let's take our break and we'll get back at, let's say break till 10:15.